and welcome to our last Electrotech in 5 class. So we were doing 3-phase induction motors last week. So we are looking at how the energy only goes to the stator from the power supply. There we are. And then magnetic field rotating here transfers all the energy to the rotor. And then there's some losses along the way. And then you get rotor output and your mechanical output. So we have to work out all these variables along the way. Variables, hello. There we go. So there's the stator windings inside the yoke of the motor. And when we allocate variables to the voltages and currents and impedances in the stator, then we use the subscript 1, okay? And everything that we do here now, all calcs are phase values, eh? All calcs for the voltage and the current and impedance. When we do the power calculations, power calcs are total, or the total values. We'll see how that works now. All right. So VP1, that means volts per phase. 1 means to the stator. So from the outside, you get the 3-phase coming in, and it's connected only to the stator, right? So the 3-phase, there'll be 3 conductors there onto the terminal box, and the voltage per phase is either one of these two, depending whether the stator is star or delta connected. There's Z per phase, the impedance is resistance plus JX, there's no capacitance involved. And then to get the current in the stator, which is then the motor current, because only the stator receives the current. VP1 over ZP1. Stator copper losses. So when we say losses, we mean energy, watts, eh? Power rather, watts. The stator copper losses, 3 times I squared RP1. Okay, the stator output is the power in minus these 2 stator copper loss. Stator copper loss and stator iron loss, these 2 stator losses. And the stator output is the rotor input via the magnetic field. Let's make a flux sign there, eh? Right, rotating. Then the rotor, all values that are given to you, you know, the resistance, the reactance of the stator, all of these values are going to be standstill rotor values because they change with the speed of rotation of the rotor in most cases. So we use for the rotor subscript 2 for standstill rotor values. So when you have a let's say that's a stator, we put 3-phase power on it. Immediately when we do that, we get a rotating magnetic field, okay, rotating at NS flux. Then it cuts across the rotor conductors and induces an EMF in them. And the rotor's still not turning yet. It's that split second before the rotor starts to turn. So here's the shaft. Turn NR equals 0. So it's a standstill value, startup value. Okay? So we have to know what these coils in the rotor, we have to work out the EMF induced in the rotor by this rotating magnetic field cutting across these coils will induce a standstill EMF EP2. Okay, that's the bottom line of it. And the standstill values for the rotor impedance, well, ZP2 is RP2 plus JXP2. Okay. Sometimes, if we're dealing with a wound rotor, it works virtually like a transformer. Eh? They give you the turns ratio N1 to N2, just like a transformer. And then you can work out EP2 in some cases if they give you that turns ratio. So VP1, which will be this one per phase, VP1 over EP2 will equal N1 over N2. See, just like a transformer, primary, secondary. All right, so now that's fine while the transformer's at standstill, but the induction motor's at standstill, but okay, hopefully it's going to rotate. So rotating rotor values have the subscript R. Now that EMF in the rotor, when it starts to turn, that EMF changes by multiplying it by the slip. So EP, the rotor EMF, when it's turning, is slip times the standstill value, EP2. This one is constant. The resistant does not change. XPR, the reactance of the rotor conductors. When it's rotating, XPR is S times XP2. So in other words, if this thing changes, then there's an effect on the impedance because it's changing. RP2 stays the same as it is. Then that's the thing. To find the current in the rotor, which is all important to do so, is just we work out this value here, and we work out this value, and then we can get the current. So the current and voltage in the rotor conductors is also AC. Yeah? So, but they ask you for the frequency in the rotor. They don't mean the rotational frequency, rotational speed of the rotor or anything. They mean the frequency of those waveforms. And the frequency of those waveforms in the rotor conductors, FR, when it's rotating, is S times the frequency. This is typically your 50 hertz, say, supply frequency. So in the stator, this will be F, would be the frequency, and the rotor, FR, would be the frequency. Rotor copper losses is 3 times these phase values of I squared R. So this is all now power. Now these two are very important. Rotor copper losses is S times rotor input power. So we're talking about power, eh? Watts. All of this is in watts. Rotor copper loss is also S over 1 minus S times rotor output power. Make a note of those. You will always use them. We don't use rotor iron loss. Okay, let's go with that for now. Oh, there's one more thing. The torque. The torque on the shaft of the rotational force. On the shaft of the induction motor, we rearrange this generic power to torque equation, and I'll make torque the subject of the formula. So torque is rotor input power over the synchronous speed, or torque is also rotor output power over the shaft rotational speed. So it makes sense. Eh? Output is the shaft, use the shaft speed. The input is where the magnetic field is cutting the rotor bars or rotor conductors. So you use the magnetic field speed. All right. So if you've got one At standstill, this is a very common way of them giving you this value of EP2, the standstill EMF induced there. So they're saying that across the slip rings here, that if it was an open circuit, then you'd measure with a voltmeter between, say, red and yellow, or any of the other ones, you'd measure 100 volts. That's what they're saying. Okay, but of course, for this induction motor to work, we would then have to short circuit these slip rings. When they say rings are short circuited, that means normal operation. It's just a way of giving you EP2. So they give you this line voltage here. All right, it's 100 volts. Okay, we'll come back to that. So then the rotor winding is star connected. It's always star connected. Now they say the reactance of the rotor at standstill. You see, they have to give you a reference value for the reactance, so that when the rotor is turning, we can work out SXP2. Because at a certain slip, obviously, we have to have some sort of rotation for there to be slip. NS minus NR over NS. So you see, as soon as they give you like a speed or a rotational speed, or sometimes they give you the slip like that, then if they just gave you the speed, you'd have to work out the slip. It's the first thing you do. You can't work out anything on this thing without working out the slip first. So then let's see here, leakage reactance at standstill is 1 ohm, and the resistance, 2 ohm. Rotor current when the slip is 4%, so that slip equals 0.04, and the rings are short circuited, i.e. normal operation. So first thing you do, the first thing you would have done is if they gave you the rotational speed, they say the motor is turning at 1,400 RPM or something, then you would have to work out the slip first immediately. But okay, they give it to you this time. So EP2, the standstill, is VL over root 3 because it's star connected in the rotor. So we haven't shown the stator here. So the stator here, not shown. This is just the rotor. They're not connected in any way whatsoever. All right. So EP, when this thing is rotating, you know it's rotating because it's got a slip that isn't equal to 1. So is S times EP2. So it's 0.04 times the standstill EMF. Is that just small numbers, eh? So now we've got the EMF. All we need is the impedance, then we can work out the current. And then if you want the current at a different, want the current at a different slip, then you can do it. You just do the same calculation. If they ever ask you to work out the startup current, if they say work the current at startup, S equal 1. That's what they mean. So read S equal 1 when they say at startup. And they often do. All right. So we were working out XPR. This S times XP2. This 1 comes from that 1 ohm. Then we work out the impedance. And now we can work out the current. As easy as that. To make the voltage or the EMF our reference point, our reference angle. And now we have IPR of 11,319 amps when this thing is rotating, when it's doing its work. Then, okay, now the slip and IPR, well, we have to same one, but now we're going to work out the slip and the IPR when the rotor develops maximum torque. Now, the maximum torque condition is when S times XP2 equals RP2. That is your max torque condition. So how do we get that? We rearrange this thing, yeah. So S equals RP2 over XP2, which is comma 2 over 1 equals comma 2. So you see, if they give you any other condition, you must use that to work out the slip. And it'll be this one, maximum torque. So now you do exactly what you did in part A, just with a different slip. That's all you do. So S times EP2 this time. We've worked it there. And then R is constant, but this time we have to use our S times XP2. You see why they give us standstill values? So we can work out the current at all different conditions, under all different conditions. Then we just work out the current like that. So you can see the current's much higher at maximum torque. All right. So that's the kind of questions that you get with these. Then the other type of question, oops, let's see, all right, it involves power. So in this case, so again, they give us this story about 500 volts between the slip rings on open circuit. So if it was open circuit here, you would have got 500 volts line voltage, eh? So this is our line volts. And it's always star connected. So you always get your EP2 like this per phase, divided by root 3. So I calculate the current in the power factor, you see, at standstill. You immediately write S equals 1. When is joined, So what they've got now, that's why you have these slip rings, is external starter resistors. Just to limit these high startup currents. Now they've got this one. Usually it's just resistance. For some reason they put reactance in it, which kind of defeats the object. You only really want resistance, so you don't want to. So this is the rotor impedance, and this is the starter impedance. Should be really puzzling to me why they would have reactance, but so be it. So this 0.04, I've already calculated, is 12.56 ohms with our 2 pi FL. All right. So now all you do is take this phase impedance over here, this one over the starter, hey, and per phase, you just add this one to that one, because if you follow this line, you'll see it's in series with it, hey, in that circuit. So now we've added startup resistors. So EP2, as usual, we do this using that line voltage. So EPR, now, what's that 1? It's because we're calculating everything at standstill, at maximum slip. Just that millisecond before that rotor starts we want to see, are these resistors working? Are we measuring whether it's doing its job, and is it going to limit the big startup current? That's what we're doing here. So the Z would be, now we add this 2 to this 10 over here, the resistances, and the reactances, hey, 12.56 and 12.56. Oh, why have I got 7 there? Okay, it doesn't matter. You get the picture, hey. Anyway, we add those, and then now we've got the total impedance in that rotor circuit at startup. Now, that's it. Then we just work out the current. So all you have to do is get that and that. Or rather, no, that and that. And then you can work out the current. And the power factor, you always put your phase EMF at 0. So relative to that 0, you've got a minus 67.92 degree angle for the current. We've got there's our E, PR, and now this one is down here, hey. There's I, P, R. Lagging. Current is lagging the voltage. So the power factor is cosine of this angle between the voltage and the current, and it is lagging. So this one, we just work out the rotor speed quickly. So nothing much there, but just with what they give us, if they ask you anything like frequency, speed, this should be NS, synchronous speed, pole pairs, and you use that stuff always to get this NS. Now, once you have that, you see in this case, let's see, we have to work out the rotor speed, the actual machine's rotational speed. So if we rearrange that, then NR is 1 minus S times NS. See, S is always a little fraction. So it makes this thing always a little bit less than that. Otherwise, it won't work. Okay, so there we have the rotor speed. Now let's do this energy flow. Rotor I squared R loss. So in other words, rotor copper loss. Rotor copper loss. This is your I squared R loss. And now you do it for the whole machine. So the rotor output. So how are we going to get this out? We haven't got current. We haven't got resistance. So we've got a bit of a problem. Hey, you remember those two important formulae that I told you? The rotor copper loss, let's call it PCU for copper, is S times rotor input. And rotor copper loss is also S over 1 minus S times rotor output. And you often, you work out the copper loss by using the rotor input power or the output, sorry. Yeah. So rotor copper loss is, let me just see, the rotor output is the motor output. And they tell you that the output of the motor is 20 kilowatts. That's P out of the whole motor. There's 20 kilowatts there. If they tell you it's a 20 kilowatt motor, it's not the input power, it's the output power. Always. It's rated at 20 kilowatts. It is a 20 kilowatt motor. It's always the mechanical output power. So we know that, and we know the frictional loss. This stuff here is 250 watts. So if you're working with this power and you're working in this direction, you must add power. If they give you power in or something and you're working in this direction, you must minus power because the power in the motor is getting less and less because there are losses. Okay, rotor output is motor output plus frictional loss, that plus that equals rotor output power. So we have this. We worked out, didn't we? No, they give us slip of 0.04. Then, of course, we can work out now the rotor I squared R loss. Sometimes they give you the means to work out the current and the resistance. And then it's a sort of a sneaky way of working out the rotor input power. But it's often, these two are used all the time, right? So, okay. I think we can't do anymore. We've got to go on to that last topic now. All right. All of these are in the slides, all of these calculations. All right. So we have to do this last module. It's a short module, but yeah, needs to be done. I'd like to do more calculations with you. That's what I like. I could just do calculations all day. But unfortunately, time